In this third video, I'm just going to look at a slightly different concept of connected particles. As you can see, the particles are still connected, and we're going to have our light and extensible string and our smooth pulley. But in this case, one of our particles is resting on a smooth surface and the other one is hanging over the edge. Now, this is still exactly the same as a connected particles question. We would mark on our tensions and accelerations in the usual way. So, for example, we know using common sense if this system was released, the 5 kilograms would drag the 3 kilograms over the edge. So we would be accelerating in this direction. And obviously the concept of light and extensible strings means acceleration is constant throughout. And then if we were drawing our tensions in, well, obviously from the 3 kilograms perspective, there's a tension or a force trying to pull it over the edge. And from the 5 kilograms perspective, there's a tension trying to pull it back over the top of the pulley. And obviously now we've got our connected particles in position. Again, we would look at it as two separate situations. So we have this situation that's actually on the surface, and then we have the second situation which is actually being pulled over the edge. And again, all we do is we apply F equals ma in the direction of travel. So if I was going to stick with the particle that's resting on the smooth surface, I would apply F equals ma in the horizontal, in that direction. And as you can see, the force acting to the right is tension. Now, because this is a smooth surface, there's actually no force acting, holding it back, because the surface is perfectly smooth. It will move without resistance. If you wanted to be ultimately very accurate about how this diagram should be drawn, you would obviously have your 3G towards the centre of the Earth acting downwards, and you'd also have a reaction force of 3G acting back up as per Newton's laws of equal and opposite reactions. But neither of those are acting in the direction of travel, or in where we're resolving F equals ma. So F equal ma will just be T is equal to 3a. If we now look at the second situation of the particle hanging over the edge, well, we apply F equals ma in the direction of motion. And now, obviously, we've got the 5 kilogram particle. Well, there's going to be a force of weight of 5g, dragging this particle to the centre of the Earth, or vertically downwards. And applying F equals ma, we would have 5g is acting down, tension is pulling back, resisting the motion. So that's minus t is equal to 5a. Now, this is surprisingly easier than the example we've just looked at, because immediately we know that tension is equal to 3 lots of acceleration. So I can take that and substitute it directly into the second equation. So I'm going to end up with 5g minus 3a is equal to 5a. So in this case, 5g is equal to 8 times acceleration. So 5g divided by 8 ms to the minus 2 is my acceleration. Now, I already know that t is equal to 3 times acceleration, so t is going to be 15g divided by 8. That's 3 times 5g over 8 newtons. And therefore, my solution is quite straightforward. In Unit 2, you deal in majority of situations